So when we want to find the value of a derivative at a point, we don't need to find that whole equation there of the derivative if we just want the numerical value. So we've got this formula. This is just kind of a modified version, f of c, c being a certain point. Little typo going on here. This should be at a point c and f of c. All right, how about that? So the same formula, but instead of having an x, we've got a more specific value of c. So let's see how that works. So here we got a function. We want to find the definition, or use this limit definition to find f prime of 1. Well, f prime of 1, we know, is the limit as h goes to 0. And we're going to have f of, now our c value is 1, so f of 1 plus h minus f of 1 all over h. Now, it's usually not a good idea to do separate problems, but this might be a nice place to do that. F of 1 is just 1 over 1 plus 1, which is 1/2. F of 1 plus h is going to be 1 plus h on top. And on bottom, when we plug 1 plus h into here, we're going to have 1 plus h plus 1, which is 2 plus h. Now we can substitute those things here. So this limit is going to be the limit as h goes to 0. F of 1 plus h is 1 plus h all over 2 plus h. F of 1 is 1/2 all over h. Still can't substitute h in here because that's a problem there, but we know how to deal with this now, right? Multiply the top and bottom by the common denominator, which is 2 times 2 plus h. 2 times 2 plus h. All right? And so that's going to, when we distribute this here, don't forget to distribute. Okay? We still got the limit as h goes to 0. And we're going to have those denominators cancel a bit. When we multiply it here, the 2 plus h is going to cancel out, and we're going to be left with 2 times 1 plus h. Don't forget, multiply 2 times this numerator. And then minus, and when we multiply it here, the 2 will cancel, so a minus the 2 plus h. Okay, 2 plus h all over h times 2 plus h. All right. Now let's clean this up a little bit more, running out of room here. Zoom in. The limit as h goes to 0, and we have 2 plus 2h on top when we distribute this out, minus 2 minus h all over h times 2 plus h. That's an h. And what's going to happen here? The 2's are going to cancel. They're gone. And then you have 2h minus h, which is h. So we're down to limit as h goes to 0 of h over h times 2 plus h. These h's cancel, leaving 1 behind, and we can plug in 0 here now. And when we plug in 0 into this h, we get 1 on top, and on bottom 2 times 2 plus 0, which is 1/4. So the slope of the tangent line when x is 1, the slope of the tangent line will be 1/4. So we just found out that f prime of 1 is 1/4, and that is the slope of the tangent line at 1/4. All right, so one little application here. Rates of change. So we're going to have 2 types of rates of change here, okay? We have the average rate of change. The average rate of change tells us the slope of the secant line, all right? So the secant line, if you remember, if we have a graph and the secant line goes through 2 points. So if we take 2 points and we find out that average rate of change, the slope, we're just really finding the rise and the run between those 2 points. And that is the slope, which we call the average rate of change on that interval. Now the instantaneous rate of change is what's happening at one point. So if we have this graph here, we want to find out what's the change right there. Well, that's the instantaneous rate of change, the speed right at that moment, all right? And that is what we call the derivative. The derivative is the rate of change as the limit as h goes to 0. That's the instantaneous rate of change there, okay? So consider this. We've got a skydiver jumps out of an airplane from 5,000 feet. He drops his camera out of the airplane at the same time. And so the camera is falling without any air resistance. And so if we use this formula here, here's our formula from physics. Position S of t equals negative 16t squared. So let's find the average rate of change for the first 5 seconds. Well, the average rate of change is just the slope. So for the 5 seconds, the change of y over the change of x, a little typo here, just noticed. Typo number 2. This should be the change in y over the change in x. Make sure yours says that. Okay, so delta y over delta x. So we have f of 5 minus, and actually let's go s of 5 because it's the position, s of 5 minus s of 0 all over 5 minus 0. So we know we went 5 seconds. So for 5 seconds, and if we plug in 5 here to t squared, we have 25 times 16. All right, so that would be negative 400, and when we plug in 0, we get 0. So 400 divided by 5 would be 80, and the negative here means that we're just going down because we're falling out of the airplane. So negative 80, and so this is feet per second. Whenever we take the derivative, or the average rate of change, okay, so we have feet on top, that's position, seconds on bottom there, all right? So now, what is the instant rate of change at 5 seconds, all right? So we're falling out of this airplane and got this camera falling out of the airplane. What is the instantaneous rate of change, okay, for this graph, all right, which actually goes like this, negative 16t squared. That instantaneous rate of change at 5, what is that slope? Well, to do that, we got to find the dy dx, okay? So how do we find the derivative? We want to find s prime, and we can use our shorthand one here because we actually want s prime at 5, so this might save us a little bit of work. And so that's the limit as h goes to 0 of s, in this case, of, we have 5 plus h minus s of 5 all over h. Now we know what s of 5 is. We already found that, s of 5. Plug in 5 and we get negative 400. Found that up above. S of 5 plus h is just going to be negative 16 times 5 plus h squared. H there. So substituting here, we get the limit as h goes to 0 of negative 16 5 plus h squared minus 400 all over h. So what do we do from here? We can't just substitute 0. So we need to go ahead and we need to multiply this top part out here. And we're going to have limit as h goes to 0. We'll have 16 times, negative 16 that is, 25 plus 10h plus h squared minus 400 all over h. And then we have, when we distribute this out, I got one little mistake here. Have you found it? Did you see it a few moments ago? Up here we have minus s of 5. Well, s of 5 is negative 400. So we got minus negative 400, which is going to make plus 400, which is going to make plus 400, plus 400, and that's good news because here our 400s are going to go away, and then this h is going to cancel both ways. Make sure you cancel it on both of them. All right, so the limits we have, the limit as h goes to 0, what's left? Negative 160 minus 10h. Okay, so we canceled both ways. Cancel the h here and cancel the h out of that term, and the 400s go away. Now, what happens as h goes to 0? Well, as h goes to 0, this here is going to 0 because it's 10 times 0. And we're left with negative 160. And there you have it. So we're going to go negative 160 miles per hour, or sorry, feet per second, at that moment. Right? So at that moment, we're going a whole lot faster than the average rate of change. So totally different story if we're talking average rate of change or the instantaneous rate of change. Okay? This is an overall average. This is the instantaneous momentary change that's going on there. All right? Well, that gives us some tools there to use when we're finding an exact value or a numerical value of a slope using the definition of the derivative. Hope that helps. Keep it up. We'll see you next time.